medium load hours, and the peak load condition we have applied that 1500 hours, and we have throughout the performance of system we consider that total throughout the system by applying the 50% and the 100% and 160% of the load by considering the different types of load models. So, as far as concerned here, the load flow studies of the RDS, I already told that the distribution system load flow studies are different than the transmission system studies. Transmission system load flow studies. As far as concerned by the X by R ratio, the design of the load flow studies that is based on the X by R ratio of the system. So X by R ratio is very high in the transmission system, and the X by R ratio is very less in the distribution system. So resistance is high and the reactance is high in the transmission system, and resistance is very high in the distribution system as far as the conductor size is concerned, the area cross section of the conductor. So here we have considered the distributed generation. The generator will generate the power at the generating station. As from there we have term the what is the distributed generation. We have to generate the power rather than the in the generating station. We can generate at particular location where the we have to require the more power to compensate the large demand of the power at the consumer side. So here the distributed generation means we have to generate the power at particular location where the large amount of load demand is required, means we have to compensate the load demand. Then that particular place we have to integrate the distributed generator to compensate that particular load. Because of that we have to reduce the line losses, means whatever the power coming from the substation we have to generate at the particular location to compensate the high demand of the load. So line losses, by this the line losses between the generating station to that particular high load we're going to compensate by placing the distributed generation. This is the basic definition of the distributed generation. We have to generate the small scale power, means at the particular location at the consumer side, not the generating side. This is the distributed generation definition. So we have to refer that the different load flow studies and the distributed generation, reference 6 and 7 we may refer for the better understanding purpose. So these are the radial distribution structure. In the distribution system there is no loop in the buses, means one bus is connected to other bus and other bus is connected to, here we consider the bus 1 2 3, bus 1 is connected to 2 and 2 is connected to 3. There is no loop in the distribution system, that is the radial distribution system. In the transmission system there is a loop structure is there. As far as the transmission system is concerned, is the way the main concern is the reliability, means one bus is going to, one side of the generation is going to fail, then other side of the generator is going to generate and distribute the power through the other fail side. But here in the radial distribution system, if any distribution line between the two buses is going to break out, the power going to stop in the next buses. And there is no structure of loop in the distribution system. So these are the main difference between the transmission as well as the distribution system. So here we have used that different level of distributed generation. We have used that is the micro DG, small DG, medium DG and large DG by considering the size of the distributed generation. So micro DG will going to generate the power 1 watt to 5 kilowatts, and the small DG we have considered that 5 kilowatt to 5 megawatt, and the medium DG we have considered that 5 megawatt to 50 megawatts, and the large DG we have considered that 50 megawatt to 300 megawatts. So from our presentation, so here we mainly focusing on the small DC and medium DC, that is the 5 kilowatt to 5 megawatt and the 5 megawatt to 50 megawatts. These are the generating levels which are mainly focusing on this presentation. And the types of DC based on the injection and the congestion of power from the substation. So we have divided into 4 types, that is injecting the only real power DCs, injecting the only reactive power DCs, injecting both real and reactive power DCs, supplying the reactive power and consuming the supplying the active power and consuming the reactive power. So in this case, our main focus is that we are considering the only injecting real power disease for the distribution system case, as well as the injecting only reactive power we have considered in the transmission system. Why? Because transmission system offer the high reactive power rather than the real power loss. The distribution system offer the high real power loss rather than the reactive power loss. So here we have considered here only injecting the real power DGs, as well as we have considering the capacitor by injecting the reactive power to improve the voltage profile. This voltage profile always are the power factor improvement in the distribution system. But this injecting the reactive power in the distribution means radial in the transmission system by compensating the only reactive power loss in the transmission system. But by injecting the reactive power in the distribution system means it is going to reduce the reactive power loss, as well as improving the voltage profile, as well as improving the power factor correction in the distribution system level. So in the reference site, we have to refer the reference site for the better understanding of the types of DG based on the injection and consumption of the power which are given in the reference site.
Okay, sir.
So here, from that we have applied the load flow studies to the transmission system as well as the distribution system. So in the distribution system, load flow studies is different than the transmission system. Here we use the direct approach load, and we also used the backward forward load flow studies. But in this case, we have used the direct approach load flow. From that, we have to place the DG by in the load flow itself. But the load flow studies, we have the random component, but each iteration we have get the each different values. But we have to run the 100 iteration, but 100 different values we get. But which value is optimal? It is very difficult to find out the optimal values, means optimal place, optimal size, and the real power loss, reactive power loss, voltage stability index, as well as the voltage profile, mean total voltage deviation. It is very difficult to uh, it is very difficult to find out the which value is better in the which iteration. It is the very difficult part in the load flow studies. By that purpose, we have considered that meta heuristic algorithm to find out the at particular iteration out of the 100, at particular one iteration, it gives the best location, best size of the DG, as well as the optimal power loss, reactive power loss, voltage stability index, and total voltage deviation. But at that particular instant, the system of the system performance is going to improve. So for that purpose, we have used the meta heuristic algorithm uh, to get the optimal solution rather than the random solution. So here we have used that in this case we have considered the in the literature. I have observed that before meta heuristic, the single objective optimization is there by using the meta heuristic algorithm. But another case is that we have to nowadays the most of the system we have considered that the multi-objective optimization. So in this case, the work 1, 2, and 3, I have considered that I have optimized the multi-objective problems to combine to the single objective function by using the single objective optimization algorithm. So here, how I single objectives, multiple single objectives is combined to form the single objective function to use the single objective optimization algorithm. So here we have used the weight factors, means weight factors to add the multiple objectives to combine to form a single objective function. So later part I have explained that is how to
and
choose
that is also and that is also to bring these particular different optimization function values to the same level. So that is W1 is multiplied, W2 is multiplied, W3, W4, like that. This is something like a procedure to convert the multi-objective to a single objective one using these weighting factors like W1 to W4. That is what is written over here, and that is to bring them in the same platform. Now, what are these four objective functions? So So one is related to the minimization of loss,
వెళ్ళండి
like that. So first objective is going to minimize the loss of the system, and that is expressed by equation number 4. And then the second objective is the minimization of this Q loss. That is what is the reactive power loss. That part is to be minimized. So it is defined in this particular objective option 6, equation 6. And then the total voltage deviation. That is how much is the deviation from the nominal value. That is in the form of a minimization problem, and that is expressed in I8. And the final one, that is the stability index, voltage stability index, PSI, and that is expressed by this particular minimization problem by 9. Now the thing is that all these four objective functions, they are having different values at a particular moment, but how to bring them on the same platform, that's why it is multiplied by this weighting factor W1, W2, W3 and W4 by suitably choosing these values of W1, W2, W3, W4 depending upon the system configuration. And these are the constants. Constants we are having two types. One is equality constant, another is inequality constant. So equality constants in the sense that this is equal to this one, this is equal to this one. But in terms of inequality, what is the range? That is, what is the minimum and maximum value of that particular value, that is expressed in terms of voltage, in terms of reactive power, in terms of real power, like that. The first one is related to the voltage, that is how it is optimized or is to be constant within this particular limit of minimum and maximum value. That is restricted by Vi, say Vi mean is less than equal to Vi less than equal to Vi max for that particular IF pass or IF norm. And then the real power is expressed by the second row, and accordingly the reactive power limit, that is also by third row, that is Q mean less than equal to Q less than equal to Q max. And then this active power balance, that is in this particular fourth row, and reactive power balance on the fifth row. Now we will be coming on the different test systems that we have adopted. So here it is a very typical two systems. One is IEEE 33 bus, another is Brazil 136 bus. So 133 and 136. 136 is quite large number of nodes are there or bars are there. And these are the system configurations that we have chosen, and those also taken from the literature. Not we have designed anything of our own. Only thing is that we have to feed these particular values to the program that we are developing.
So these are the two test systems we have considered to test the different algorithms, meta-heuristic algorithm to measure the performance of the system by P loss, Q loss, TVD and VSI. So real power loss, reactive power loss, total voltage deviation and voltage stability index. So here in the objective function, we have observed that here all the objective function by considering the weight factor method, that is weight factors we have we are going to determine the weight factor by analytic hierarchy process. So that is the multi-criteria decision method to which objective function is going to more priority than the other objective function. By considering the multi-criteria decision, we are making we are determining that the weight factor, that is W1, W2, W3, W4, which are given in the equation 3. So in this case, in this method, we have the disadvantage that if we are going to minimize the one objective function, then all the objective function we are going to convert in the same minimization function, rather than if objective function is going to maximization, so all the other function we are going to convert in the maximization function. This is the main disadvantage of this method. But this method is give the accurate values. Then we are going to optimize the multi-objective functions, means multi-objective function by using the multi-objective algorithms. Here we are minimizing the multiple objectives with single objective function with the help of the weight factor method. The weights of this objective function we are going to determine by the analytic hierarchy process, that is the multi-criteria decision making approach. So here In this case, here the objective function 1, objective function 2, objective function 3, and objective function 4. This all the four objective function I have considered in the minimization function. So objective function 1 is the minimization function, and objective 2 is the minimization function, and objective 3 also is the minimization function. But objective 4, we have considered that this is the maximization function, but one by that maximization we have converted into the minimization function. So all the four objective function we have converted into the minimization function, and with the help of is subjected to the some constraint that equality and inequality. So these are the two test system I have considered to determine the performance of the system by placing the distributed generation and the shunt capacitor in the test system 1 and test system 2. So the details of the line data and bus data these two systems we have get in the reference number 10 to 11 for the test system 1, that is IEEE 33 bus, and the test system 3 with test system 2 we have considered the reference number 12.
And if any one of you are interested, you can go through these particular three references. Those are very helpful as far as the data is concerned. For as Balu has told, reference 10 and 11 for IEEE 33 bus, and reference 12 you can get it for 136 bus. That is Brazil system. This is a large system, so you can adopt it. So you see the configurations. This is a typical system that is framed. The figure 2 is the SLD of the IEEE 33 bus systems, and the figure 3 is the single line diagram of this practical Brazil 136 bus systems. Normally what happens whenever you are doing a particular work on 33 bus systems, the reviewer are giving some comments that why it is not applied for a large system. Okay, so to adopt that particular large system, you can think of this Brazil 136 bus system, because it are having so many number of nodes over there, and it is a typical system designed to check the applicability or visibility of any optimization algorithm, whether it works for a large systems or not. Okay, and normally what happens if we go for the single load flow studies also, that you will find that this is typically done in IEEE 14 bus systems, 30 bus systems, then 57, 118 bus systems like that. So now people are also working on IEEE 300 bus systems also. So here this particular radial distribution system reconfiguration applications, as far as this particular part is concerned, this 136 is a pretty choice for the researchers. So you can think of. And in our papers also we are given this particular single line diagram of this particular model, so that you can think of how the program can be developed for this system like Brazil 136 system, which is a large Jaguar. Now we will be going to the in details about the three works that we have adapted. The same work with different algorithms, like as Balu has already told, and I have also told in the introductory part, that one part will be CF PSO, that is constriction factor PSO, and Balu has already told that how these two parameters W1 W2 are chosen over here, and that is going to determine how the algorithm is going to converge. That is one particular thing that I have already mentioned, that if it is dependent, that performance of the algorithm is dependent on the PSO, on certain parameters, then it will be very difficult to tune those parameters in certain cases. But in certain cases, you can also have that, you can get the good results. So as we are going to present for this particular work one, that how with a properly tuned CFSO, that is constriction factor based PSO, how these two systems, that is 33 bus and this 136 bus systems, how these results are going to have the better one. And now we are not satisfied with this particular work, so that's why the reason why we have moved for work 2 and work 3, and gradually you will explain. Okay, and by this time, if you are having any queries, you may ask by this time. Otherwise, we may proceed for the problem formulation for work 1, work 2, and work 3, how these particular works are done. And for those who are new in this particular field, whenever I'm once again telling you that whenever you are going to present the data, that is going to be related to how these particular results are going to be helpful for the others also. Okay, so any questions?
Up to this, you may have any queries. Please ask.
Okay, then we may go forward.
So in the work one, we have considered that meta-heuristic optimization algorithm, that is constriction factor particle sum optimization algorithm, to place the optimal site and sizing of distributed generation as well as a shunt capacitor bank the radial distribution system. So here we have considered the two test system, that is IEEE 33 bus and the practical Bayesian 136 bus RDS. So by employing the by placing the distributed generation at optimal location and size, for this purpose we have used the constriction factor particle sum optimization, and after that we have to compare the performance of the CPSO algorithm with another different algorithm. So here, first one, the main contribution of this work one is that first we have to use the CPSO algorithm to place the to obtain the optimal position and size of the DG and SC banks. And another is we have to after applying that, whether we are getting the optimal results in terms of real power loss, reactive power loss, voltage stability index, and the total voltage deviation. So
And you are, as you are seeing here, you may see here that this particular work was published in electric power components and systems, because initially we started the work with this CFPSO, that's why it got published in this particular journal. You may refer it. So here we are going to tell some basic aspects of PSO. So for any optimization algorithm, what happens that you have to know that what is your objective function that you are going to handle. What is the statement of the objective function? That say it is something like an expression. So what are that associated values that you have to put it before that particular execution of that objective function? What are those values? And then also you have to put that what are the constraints that say you are having certain parameters, say x1 to x5. Then x1 to x5 has got some minimum value and maximum value. Then within this minimum and maximum values, only those values will lie. So that is very apparent. Now with this particular formula, that minimum plus rand into max minus mean, if you use that one, then automatically all the values that will be coming for this x1 to x5, that will be lying within that minimum and maximum values. So let me repeat, minimum value of that particular parameter plus random into max minus mean. So max minus means what is the difference between the minimum and maximum, and in between you that particular value, whatever you are getting the difference, you multiply it by random value. So automatically some values will be, rand means it is a value between 0 to 1. So that value will be scaled to 0 to 1, and then what is the minimum value? So automatically this minimum always will be there. In addition to that, what is the limitation, that particular variation? So if say for example you can take the two extreme case, one is rand is 0, that minimum value will be taken as the particular parameter value, and if rand value is maximum, that is 1, so in that case that minimum plus that difference. So what is the difference? That is the max minus mean value. So that will be eventually giving you the maximum value. That is the reason why this particular parameter are chosen using those formula. So now you see you are having you have generated 5 values x1 to x5. Now put those values to that particular objective function that we have already set. Now get the value. What is the value? Because it is an initial value, it is not the corrected one. So now say for example you are having a bed cover. So on this bed cover there are say several points. So x1, x2, x2, x4, x5 is minimum to maximum value, several points. Now you have started with a particular point. Now this particular point may not be the maximum one. So what is the particular optimal one? You go to that particular one and then you choose it. Just 1 minute. Just 1 minute. So what you have to do, that you have to take the value of the objective function, that is cost function. Say I am talking about it is a cost function. So take the value of the cost function. Then
ఇవి
with that particular cost
FTP
function,
స్టార్ట్
it is
చేశాను
not the
ఆయన
optimal one.
ఏమంటారు అని చెప్పేసి
Now you disturb that particular
మీరు
parameters x1 to
వైల్
x5
ఆడుతున్నారు
as
సార్
per the rules
వచ్చేసి అటు నుంచి
that is governed by that particular algorithm. You disturb that particular parameter, and
ఓకే
then
ఓకే
with
సార్
those
వైల్
disturbed parameters in the next step, you just give that particular input to the objective function and then get the objective function value. Then what is this value of the cost function, whether it is better than the previous one or not? Better means if it is a minimization problem, then this value will be lesser than the earlier one, and if it is a maximization problem, then this value will be more than the earlier one. So our task eventually will be to get that particular value of the parameters or set of the parameters which is yielding you the minimized or maximized value of the particular algorithm. And accordingly, as per the value of the objective function that you are getting over a particular iteration, you store it and plot it in the form of a profile to have the convergence profile of that particular algorithm, that how it is functioning. So these convergence profiles will give you different aspects. In some papers, while reviewing, we will find that they are not giving any convergence profiles. So this is not a good indication that you may get it a particular value of that algorithm, but how the movement of the algorithm over the iteration is going on, that is predicted by this convergence profile. So it is very helpful in that particular sense. Second part is that how that particular optimization is moving. That is whether that particular movement is very fluctuating in nature or it is gradually coming to an end. So in between heavy fluctuations means there is a heavy change in this particular values of the objective functions, and the optimization is algorithm itself is working hard to get the value of the optimal one. But if it is a smooth one, then gradually, say for example, minimization problem means over the last iteration, at the current iteration, how much you are getting, whether it is a lower one or the higher one. So if it is a lower one, automatically the objective function will move or follow a smooth pattern. And that is one point. Second point is that even if in some cases you can find that even if it is a minimization problem, the object function itself is going to be a minimum maximization problem. That means in case of gradually decreasing the value itself is going to be maximized. Okay, so that is not eventually giving you the optimal value. Okay, it happened. One story I can share with you that while coding that harmony search algorithm, initially during my research, what happened that we are getting a value, but in place of minimizing the function, it is going to be maximized. That means in a particular function, it is giving you the maximum value. That means it is starting from a lower value and going to a higher value with a smooth one. So that is also not a healthy condition. Then we checked it and it is found that there was a mistake in the algorithm, and then we corrected it, we rewrite the program, rewrote it, and we are getting the eventually the smooth optimization algorithm for this harmony search algorithm. And after that, my future researchers worked on different variant of harmony search algorithm like quasi-oppositional, then oppositional, harmony search, and like that. That was the best or fundamental one. So once the fundamental algorithm is set very nicely, then automatically the other hybrid version may come out from this particular algorithm and may give you the very good result or promising result. And as I have told that also, that initially this practice of providing the code was not there. Say for example, seeker optimization algorithm was published at my time, and that PBO, biogeographic based optimization algorithm, we worked on 1 to 2 months to code it, and then testing it take another 1 month. So automatically all these months are wasted, and now it is readily available. Just like a copy, that's what I am taking now from a what it is called copy machine. Just you pay the price and you get the copy. But initially it was not like that. And now this is the work that how a particular algorithm works, that over the iterations, whether it is giving for a minimization problem, it is giving a minimum value as compared to the just previous one or not. And accordingly, we have to check the mobility of the convergence. And here also this particular algorithm, if you take any algorithm, whatever it is, there are say n number of optimization algorithms, but all the algorithms, what you have to do, that you have to check its convergence mobility, whether it is giving better result or not, whether it is giving a smooth convergence, whether it is coming to a particular value with lesser number of iterations or not, as compared to the other comparative algorithms. Then only you can think of, and then we may go for other statistical steps, that how it is statistically sound or not. So before launching a particular algorithm, all these works have to be done on a set of well-defined test benchmark functions. Those are available in the form of some competitive benchmark functions. You have to test it. You have to test it on the real-time algorithm, real-time problem, and then only people are going to accept it. Because mathematically, once it is proved, then only it is accepted. And then also there is that no lunch free, no free lunch. No free lunch theorem. No free lunch theorem. So you cannot say that this is the ultimate one. So I am proposing next one today. Say next day Balu may come, you may come also with some other algorithms, but also testing on this particular benchmark functions with those testing attributes. Okay. So this is the way that in 1995 that Kennedy and Everett they published a paper. It was published in a conference paper earlier than this particular GA and other only the normal algorithms were there. But now onwards from 1995 PSO came, and after that once it came, so different variants of PSOs were proposed. So here there are two things. That one is that how this performance is working and what is the value of the particular optimizer function is giving. That was the two essential features. And for that there are two parts. One is the what is in between a particular group of people and what is the other people are doing. So these two aspects were covered, and accordingly the concept of W1 and W2 was taken into account in this particular work in 1995. And then 1995 Clark also modified that PSO in the form of this constriction based PSO, where the concept of this phi constriction factor is governed by this particular two equations. That is when by taking that C is equal to, that is W what we are telling, or it may call it as C also, that constriction factor C1 plus C2, and that C must be greater than 4, and this particular equation 11 will basically give you how this particular work of CFPSO was formed. Now we will be moving to different cases of the problem that we are handling. So cases 1 to 4 is like this.
So in this case, we have considered that in the work one, we have considered that 4 cases to demonstrate the application of the CPSO algorithm by obtaining the best location and size of the distributed generation as well as the shunt capacitor bank. So in this case, in the case 1, we have considered that 2 DGs operating at unit power factor, means DG1 is injecting the only reactive power, means only real power, and the 2 shunt capacitor banks installed at their optimal location simultaneously. So the case 1, we have used that 2 distributed generation, that is real power DGs, and the 2 shunt capacitor, that is 2 reactive power DGs replaced simultaneously. In the case 2, we have considered that 3 DGs operating at unity power factor and the 3 shunt capacitor operating at to inject the reactive power, and we have considered that the simultaneously to place the 3 DGs and 3 shunt capacitor banks. In the case 3, we have considered that 4 DGs and 4 shunt capacitors simultaneously, and the case 4, we have considered the 6 DGs and 6 capacitor banks. So here by choosing the number of DGs, that is depending upon the total load and total demand plus reactive power loss and the real power loss of the line. So here total demand plus losses is equal total generation of DG plus the whatever the real power drawn from the substation. So these are the power balance equation we are going to consider in the case 1, case 2, case 3 and case 4. Here depending upon the load demand, the case 1 and case 2 are considered for the IEEE 33 bus, and the case 3 and case 4 we are considered for the particle Basel 136 bus RDS. Here the load demand of the 136 bus is very high compared to the IEEE 33 bus, so that we have considered 2 DGs and 3 DGs to simultaneously place at the in the 33 bus, and the 4 DGs and 6 DGs means if you have considered the 1 DG injecting the 2 megawatts and the 6 into 2 is called 12 megawatt, but the load demand of the 136 bar RDS is more than the 12 megawatt. It is around the 20 megawatts. So rest of the power is drawn by the drawn through distributed lines from the substation. So whatever the power is there, the remaining power, that is the 6 megawatt, is drawn from the uh, substation. Thereby we are decreasing the line losses, where particular location we are compensate the 12 megawatt load. So here case 1, case 2 in the IEEE bus, IEEE 33, and the case 3 and case 4 we are considered the practical Basel 136 bus RDS. So here these are the voltage profile, comparative voltage profile we get from the different variant of the PSO algorithm. So here we consider the three different case, that is PSO, that is particle sum optimization. This is the standard one, and the modified particle sum optimization, and the constriction factor particle sum optimization. So these are the comparative voltage profile of the these two when applied to the 33 bus, when the case 1 where we have considered 2 DGs and 2 capacitors. So here from the figure A and B, that figure 4 A and B, we have observed that the CPSO algorithm CPSO algorithm get the better voltage profile as compared to the other two algorithms, that is PSO and MPSO. And these are the figure 5 A and B. This is the comparative voltage profile, means comparative VSI profile, that voltage stability index profile of the IEEE 33 bus, that is the case 1 and case 2. From this profile we observe that CPSO algorithm get the better voltage profile as compared to the PSO and CPSO algorithm, means MPSO algorithm. So here this is the comparative convergence profile of the CPSO algorithm as compare the PSO, MPSO and CPSO. The CPSO algorithm get the better voltage profile and the better VSI profile, as well as the better convergence profile. With less number of iteration, it is converted the global optima rather than the local optima. It means we get the better better objective function value. So as compared to the PSO and MPSO algorithm. And the comparative analysis for the different case of the IEEE 33 buses is tabulated in the table 5. You observe that the PSO, MPSO and CPSO algorithm. So case 1, case 2 for the PSO algorithm, case 1 and case 2 for the MPSO algorithm, and the case 1 and case 2 for the CPSO algorithm. So these two algorithms are studied and the CPSO algorithm is the proposed. So here you observe that CPSO algorithm get the better values as compared to the other literatures. We have tabulated in the table 6. You observe that the CPSO algorithm offer the better power loss and the minimum voltage profile, as well as the loss reduction. The large reduction is get as compared to the CPSO algorithm is better, is get the better results, means optimal results, by comparing the PSO and MPSO and the other state of art of the algorithms, that is GABC, analytical, CSA, FGA, BFO, CSA, FEA, PSO and MPSO. So out of these, the CPSO algorithm get the better optimal results as compared to the other algorithm which are shown in the table 6. So the comparative voltage profile for the Brazil 136 bardias, the case 3 and case 4. So in this case, we observe that figure 7A and B, the CPSO algorithm get the better voltage profile as compared to the PSO and MPSO, is shown in the figure 7A, as well as the for the case 3 and case 4. So in the figure 8A and B, which shows the comparative VSI profile of the Brazil 136 RDS. So from this profile, you observe that the CPSO algorithm get the better voltage profile as compared to the PSO and MPSO algorithm. So from the figure 9A and B, observe that this is the comparative convergent plots of the objective function for the Brazil 136 RDS by considering the case 3 and case 4. So from these figures, we observe that CPSO algorithm get the better convergent profile as compared to the PSO and MPSO. Here, the CPSO algorithm take the less number of iteration to get the optimal value. So here the table 7 it shows that the comparative analysis for the different cases of Brazil 136 versus RDS. So the CPSO algorithm get the better values, means optimal values as compared to the PSO and MPSO algorithm for the case 4 and case 3 and case 4.
Now you see when we are applying or testing this CFPSO, constitution factor based PSO, so on this particular two test systems, basically what we have shown that how the voltage profile is changing, that is for all the nodes, how whether these voltage profiles are within the specified limit or not, that is one aspect. Second aspect is what is the convergence mobility of the algorithm. Third aspect is that how the results are compared with the existing one. If there is no existing one, then you can take it some algorithms as the studied. Say here, for example, for this particular test case, we have taken PSO, then MPSO, and then we have landed down to this particular CFPSO. So these are not earlier published in this particular domain. So that's why we have studied as a PSO, basic PSO for 33 or this 136 bus, then MPSO for this 33 or 136 bus, and similarly for CFPSO, that is the proposed one on this 33 and 136 one. Okay, so this is the way how the particular results are to be produced for acceptability among the research community. Next work that we will be dealing with this application of this particular solution of this OBGA problem using HHU algorithm, considering different types of load models at different levels of load penetrations. So load penetrations we are also considering, and different types of loads are also considering, and as well as we are changing that particular CFSO domain to the HHO domain. Now let us.
So in this case, in the work one, we applied that CPS algorithm by considering the only constant power load at the medium load condition. That is 100% of load we applied at the constant power load and